Have you ever seen a monkey evolve into a man? No, neither have I. Have you ever seen a fish jump up out of the water and become a horse? No, of course not. That's because these things take millions or billions of years, right? We've been taught that the processes of evolution and natural selection over a long period of time have worked on life forms and thus generated what we see today. I'm not here to debate whether or not evolution is scientific, but I do want to look at the most important ingredient in the evolutionary recipe, and that is time. Hey everyone, and thank you so much for coming back to Hard Questions with Elena. Today, we're going to be jumping in a little bit more of a scientific direction than my last few videos. I want to break down the process of radioactive decay for you guys. Maybe you're remembering something about that from chemistry class. Maybe this is the first time you've heard that word before and you're wondering what it is. Maybe it's the first time you've heard it and you're wondering why you should even care. I'm kind of in that camp with you guys. I don't like understanding super overly complicated, difficult scientific questions and processes unless I have a really good reason. So let me give you guys that reason. Radioactive decay is the process that scientists use to date the Earth. They use this process and look at rocks and say, oh, the Earth is about 4.54 billion years old. And that's all good and dandy because science says that the Earth is really old, evolution takes a really long time to take place, therefore they're compatible. But what if there was a problem in the dating method? What if the Earth was actually a lot younger than everyone thought? This would pose a huge problem for evolution. Actually, it would make it impossible because evolution wouldn't have enough time to take place. And then we'd all be left with the huge question of, where did we all come from? That's why it's really important that they get this process right. So let's jump into it. I promise I'll try to make it not too scary. So here's how it works. Atoms are the building blocks of matter. You probably heard something about that before, right? But some atoms have a little bit of a problem, and this is that they have too many neutrons in their nucleus. Basically, all that you need to know about that is that it makes them unstable. Nobody wants to be unstable, right? So they're going to try to get rid of these neutrons. And by doing this, they become a stable atom of a different element. That's pretty much the basics of radioactive decay. It's unstable atoms ejecting or getting rid of their neutrons to become stable ones. Now, of course, like everything in life, there's always exceptions and variations and, yada, 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 the odd one out, but that's the gist of it. Scientists, if they find a rock or fossil that they want to date, they can say, well, if I can calculate how much radioactive decay has happened in this rock, then I can calculate its age. It works kind of like this. Let me give you an example. Let's say I have a rock or fossil with the atoms uranium-235 in it. Now, uranium-235 is an unstable atom that decays into lead-207. So let's say in this rock, theoretically, these are all numbers just made up off the top of my head. Let's say I have 1,000 atoms of uranium-235 and 1,000 atoms of lead-207, right? Now, in laboratories today, I can calculate the rate that uranium-235 is currently decaying into lead-207, the rate of radioactive decay. Let's say it is a minute per atom. So every minute, one atom of uranium decays into one atom of lead. Now you can do simple math, right? You can say that 1,000 atoms of lead times 1 minute per atom would mean 1,000 minutes, right? Therefore, I can assume that the rock is 1,000 minutes old. Because if I rewound time back 1,000 minutes ago, I would reach a point where there was no lead-207 in the rock. And that would be the time that the rock came into existence. Okay, pause. Take a time out. How are you doing? I know this is a lot of really heady scientific stuff. Thanks for sticking in there with me. Let me try explaining it in one more way. Actually, the first way that I ever heard it explained to me, and this is with an analogy. It's called the hourglass analogy. But basically, we could pretend that the grains of sand at the top of the hourglass are like the unstable atoms at the beginning of the time of the rock's existence before any radioactive decay has occurred. And the grains of sand at the bottom are like the new stable atoms that happen after radioactive decay. And the rate that the sand is falling down to the bottom is the rate of radioactive decay. Keep this analogy in the back of your heads as we start to look at a few dilemmas. Yes, I said dilemmas. We're going to look at 3 assumptions that scientists are making when they're assessing this process that might make their dating be a little bit off. The first assumption that they're making is that there's been a constant rate of radioactive decay. In laboratories today, we can test the current rate that one atom decays into another. But how do we know that this has been consistent throughout all of history? We didn't have anybody there millions of years ago to test and report on the rate, right? In fact, we actually have modern day examples that the rate has not been consistent. The one we're going to look at comes from the Grand Canyon. Towards the bottom of the Grand Canyon, there's a layer called the Cardenas basalt layer. So samples of the rock from this layer were taken and analyzed using several different radioactive decay methods. What this means is that they analyzed the rate of radioactive decay for potassium to argon, for rubidium to strontium, and for samarium to neodymium. And what they found was that based on the potassium-argon method, the rock was 516 million years old. But based on the rubidium-strontium method, it was 1,111 years old. And based on the samarium-neodymium method, it was 1,588 years old. It could not be all of these ages at one time, right? What this means is that 2 of, if not all of these methods would have had to decay at an inconsistent rate at some time throughout history because they're not matching up. If they could be wrong about their dating of this rock, could they be wrong about others? So let's talk about inheritance and contamination. Inheritance is the second assumption that scientists make. They're assuming that all the stable atoms in the rock were derived from radioactive decay. Back to that hourglass analogy we used earlier, what if you started off with a little pile of sand at the bottom of your counter? That would skew your results, right? It would make it look like when you went to measure how long you'd been brushing your teeth, that you'd been going for longer than you actually had. What if there were stable atoms in the rock to begin with? This would be inheritance, and we'd have no way of proving that it didn't happen. Contamination is very similar. It means what if instead someone added sand to that hourglass while it was falling? Your analysis would be off as well because all of the stable atoms wouldn't have been derived from radioactive decay. Let's look at some examples of this happening in real life. The main and probably most famous one out there is from the eruption of Mount St. Helens in 1980. Yes, this was a little bit before my time. If you're about 20 years older than me, you might have been around when it happened. Basically, the mountain erupted and a new lava dome was formed on the side of the mountain. And we witnessed this new lava dome form, right? We know that it happened in 1980, that rock was formed in 1980. So in 1990, 10 years after the eruption, scientists went up and took an analysis of the rock in their laboratories using radioactive decay, and they dated the rock to be anywhere from 0.35 to 2.8 million years old. How could this happen, right? We know that the rock was 10 years old. Well, what had actually happened was during the eruption, excess argon gas got trapped in the cooling process and skewed the results. Some of that argon being measured, they were measuring it based on the potassium to argon dating method, wasn't from radioactive decay. It was contaminated. Another example we have of this comes from a diamond that was found from within the earth, and it dated to be 6 billion years old. Now, the problem with that is that the Earth is only dated to be 4.54 billion years old. How could a diamond coming from within the Earth be older than the Earth itself? If they could be wrong about the age of the diamond, could they be wrong about the age of the Earth? So here's the deal. That's just one dating method used to date the Earth. There are lots of others out there. And if you want in a future video, we could actually take a look at some of those. But I'll say right now that 90% of dating methods actually point towards a young Earth. And of the 10% that would suggest an old Earth, a lot of them are skewed like we've just seen with radioactive decay. See, if radioactive decay is not as reliable as scientists claim, then maybe the other 90% should hold more weight and we should question whether the Earth is really so old. And if it is proven that we have a young Earth, then what do we do with evolution? See, the whole theory starts to crumble as soon as you realize the truth about time. Congratulations! You made it through a really heady video. Thanks for sticking with me to the end. I hope that this video has helped you learn more about radioactive decay and how it works, and more importantly, the severity of having it be off. If you want to see more videos about the age of the Earth or the methods used to date it, let me know by liking this video and leaving a comment down below. And as always, please remember that you guys can write me an email. Right now, I'm in the process of gathering up questions from students like you to help me know where to go with this channel, to direct my future videos so that I can answer you guys' questions. My email address is hardquestions.withelaina@gmail.com. I would really love to hear from you. Please write and let me know what you're wondering about. And as always, as I say at the end of every video, I would really appreciate you subscribing to my channel. Click the little bell notification so that you can be notified every time I post a future video. And be sure to follow me on Instagram. Have a great day. See you guys next time. Bye.